Hello, everyone. Hi. Thank you all for joining today's seminar, both everyone here in person and also those who are listening to us online. Welcome. Today, we have a very special guest, Professor Chad Mirkin. Chad is the director of the International Institute for Nanotechnology and the Rathmann Professor of Chemistry, Chemical and Biological Engineering, Biomedical Engineering, Material Science and Engineering, as well as Professor of Medicine at Northwestern University. He's a chemist and a world-renowned nanoscience expert, known for his discovery and development of spherical nucleic acid, also known as SNAs, and SNA-based biodetection and therapeutic schemes, dip-end nanolithography, DPN, and related cantilever-free nanopatterning and materials discovery methodologies, as well as his contributions to supramolecular chemistry and nanoparticle synthesis. Professor Mirkin has authored over 840 publications and over 1,200 patent applications. He has also founded 10 companies, amongst which are RSense, TerraPrint, and Azul 3D. For his groundbreaking contributions to the field, he has also been recognized by over 250 national and international awards. So it's a great pleasure to be able to have Professor Chad Mirkin here with us today to learn more about his group's work on developing megalibraries of nanomaterials with deterministic placement as well as distinct chemistries, using the platform that they've developed based on scanning probe lithography approach. So before I hand it over to Chad, I would like to remind our audience online that they can ask their questions by typing the question through the Q&A option of the Zoom, and I'll keep track of it during the seminar today. Before we start the actual seminar, I would like to start with a 5-minute video as an overview.
Meeting the growing demand for mobility without relying on fossil fuels is really one of the main challenges that we're facing. And we have to do this globally and for the whole transportation sector, not just cars. For this goal and for this challenge, discovering, designing, developing new materials is really critical.
Toyota depends upon new materials for all sorts of different purposes. You think of catalytic converters, fuel cells. The materials within those make them either efficient and useful or not. Being able to find the best materials is absolutely essential. I would argue that the world right now has been focusing on the best that they've discovered to date, not necessarily the best for a given application. So what we're poised to do through the collaboration with Toyota is to begin to look at the vast parameter set possible in terms of materials discovery, collect data from that, and then empower machine learning and AI algorithms to allow us to objectively search the materials genome and find the best materials for a given need.
Before we were using machine learning, all of our materials design was trial and error. So we had to synthesize one material and then characterize it, and then synthesize the next one and characterize that, and hope that any one of those would give us properties of interest, but we couldn't tell ahead of time.
Traditionally, we've pursued new ideas by human intuition. The things that scientists think might be interesting, they have some idea that they want to try out. By the kind of technologies that we're leveraging here at Northwestern University, it allows us to go beyond that, because not only can we use our intuition, but now we have the possibility of looking at a vast number of things that would not be possible otherwise. And that helps us look for things that we might not have thought of.
Every element has its unique properties and is different from every other element. And combinations of elements will interact with each other. Their electronic structure is influenced by the atoms around it. So depending on what they are, you can end up with a material that has vastly different properties. It can form different crystal structures. It'll have different surfaces, different electronic structures. And so there's a lot of space that has never been explored as to what the properties of these materials might be.
So the megalibraries are really a product of the modern age of nanotechnology. We invented a whole series of what we call nano printers here. Think of a printer. It's got a print head that has 100,000 or more pyramidal tips. Those can be coated with chemicals, gradients of chemicals, and then brought down, and those materials can be deposited onto a chip of interest. Being able to control particle size and shape on the nanoscale within the context of a megalibrary is very important, because many of the active catalysts that go into fuel cells, that go into catalytic converters, that are used for catalyzing all of the important processes out there are nanomaterials. 1 nanometer would be, take a dime, slice it on edge 1,000 times. Take one of those pieces, slice it another 1,000 times on edge. That's 1 nanometer thick.
Nanoparticles have very unique properties in terms of their catalytic activity. They make for good catalysts because they have a high surface area to volume ratio because they're so small. So ideally, when we make nanoparticles, we're able to make particles that have a lot of available surface for catalyzing reactions and use less of a valuable material like platinum, for example, that goes into a fuel cell. The more active a catalyst is, the more power it will produce for less fuel. So it basically means the fuel cell will be more efficient.
We're in a really unique position to take this all the way, to think about how we not only discover materials in a new way, how we create this platform, but ultimately how we deploy this platform in a company like Toyota to really make a difference in their business, and figuring out how we can strengthen the relationships between the company researchers, the company business folks, and the people on the ground at the university doing the discovery work would be really quite powerful, because it would allow us to streamline how we go from this called fundamental discovery process to real applications that can make a difference in Toyota and around the world.
So research partnerships between universities and organizations like Toyota are critical because universities have the freedom to explore and have the scientific curiosity to really drive forward the frontier of human knowledge. And what we can bring to the university partnership is a concern about making the best technology we'd like. So where those two things intersect, where the interest in providing technology for society and where the frontiers of human knowledge are, that's really where we can come together and do something really valuable.
What's exciting is we don't know what the limits are. We don't know what the best performing devices and technologies that we can make can be. And so there's always this idea that there's something better out there if we just look in the right place. And so it might be that we look for a long time and never find it, but the possibility that we might is what's exciting.
So with that very interesting video, Chad, thank you for being here today. We're very excited to hear your talk.
Okay, great. Alrighty, so I'd like to show that just to set the stage for what I'm going to talk about today. These guys, Toyota, came to me and kind of found me after we'd published several papers and said, look, you guys are making materials faster than anybody's ever done before. Those materials are an interesting source of big data. We have a big AI team here, and we'd love to learn how we can mine that data to begin to make predictions about what materials will serve needed purposes. And at the same time, we were thinking about that as well. And in fact, we'd built another company, a startup company that launched about a year ago called MatIQ or Matique. And I'm going to talk a little bit about that as well. But I wanted you to get a feel for what this is ultimately all about. I mean, most of the message you've just heard in 5 minutes, but I'm going to go through the detail of ultimately how we got there. Before I do that, though, I want to thank the assistant professors up here who are not only my hosts here, they turn out to be my medical team. We had a slight glitch last night. I ended up in the emergency room. Got to see your wonderful hospitals here until 4 o'clock in the morning. And they were fantastic in terms of getting me through that, and I very, very much appreciate it, and everything's gone off now without a hitch other than leaving Tim stranded at the bar of Legal Seafoods. Okay, so everything I'm going to talk about today really starts with an interesting discovery. You have to go back to 1999, and it was, I think, an example of at least how I approach science, and I think the way new people should think about approaching science. I had never worked with an atomic force microscope before going to Northwestern. They were just coming online as commercial tools. But I thought these were really powerful tools, and we ought to learn how to use them. And remember, they were tools that were developed primarily as readers to get topological maps of surfaces on the nanoscale. And they were very powerful tools. We came along, and through some work over a few years, figured out that we could transition these types of tools from readers to writers, and where we could use the tips to locally control chemistry by taking advantage of what was considered a major problem at the time. And that was that in air, water will collect at the point of contact between tip and surface. And that water will suck the tip down and convolute any measurements you make thereafter. As a chemist, I looked at that and said, hey, that water could actually be used as a solvent, and the tiny little droplet could be used as a reactor. And if we put molecules on the tip that could chemically react with the surface, we could locally control chemistry underneath. And that was the birth of dip pen nanolithography. And you can see what it allows you to do is, at least in cartoon fashion here, is make monolayer type architectures on the left. But over here on the right, you can actually see the nature of this process. It's diffusion limited. These are monolayers of alkane thiols on gold. Great prototypical type of reaction. But really anything that will react with any surface can be used as an ink and substrate combination. And you can see the longer you hold the tip in contact, the bigger the feature is. It's just diffusing from the tip to the surface, and you're now making nanostructures at will. And from my standpoint, this is the early start of the modern age of nanotechnology. And this became, at least from my perspective, an ideal tool to study the consequences of miniaturization. And so we were off to the races. Over the course of now over 20 years, almost 25 years, a lot's happened. And we learned a lot about this, and sure enough, it was commercialized ultimately, and these types of tools now are used all over the world for doing exactly what I said, making miniaturized devices, to studying the consequences of miniaturization, compatible with soft matter, compatible with hard matter, can do it at the point of use. At the same time, here in Boston, we had people like George Whitesides developing this technique called contact printing, micro-contact printing. And the idea there was that you could, in a parallel fashion, build microstructures over surfaces. A lot of people in the early days thought these were competitive. They're not competitive, they're highly complementary. They do completely different things. One allows you to pattern over large areas, but not very high resolution. The other allows you to print over very tiny areas and is extraordinarily high resolution. You get down to 10 nanometers in terms of feature size in the case of dip pen. But it also put a spotlight on deficiencies, right? So the question is, could you get the best of both worlds by somehow merging these capabilities? And that's what we decided to do. We said, well, wait a second. We don't need an AFM to do this type of printing. We just need a translational tool. And we need not just one tip, but many tips to pattern over large areas. So the idea was, let's build a contact type of pyramid array that could be effectively our AFM, mounted on a glass substrate, something hard so that it would be level, because being level is critical in terms of working on the nanoscale. You blow things up, things look like Mount Everest, right? So you really have to be quite good at this. And then let's insert that into the translational tool driven by piezos and use that as a way to move back and forth with nanometer scale resolution and up and down in a way that you control contact force. And that was the birth of something called polymer pen lithography, or cantilever-free scanning probe lithography tools. That turned out to be a really big advance because it really changed the way we thought about these types of tools in many ways, going from a serial tool to a massively parallel tool. Thinking about how we simplify the process. Polymer pen lithography now works with as many as 11 million tips working in parallel. Every tip is working. It's an incredibly forgiving process because you can push until the tips are all in contact, allowing everything to get in contact and then make uniform feature sizes based upon contact force. I'll get back to that in a second. It also changed the way we thought about how we could do other things. For example, in the case of beam pen lithography, that's a variant of polymer pen lithography where we don't transfer molecules, but we use light driven through the pyramids where they become light pipes and lenses where we can address the back of the pyramid macroscopically or microscopically, squeeze the light through the tip and work in the near and the far field, and now have a photolithographic type of tool that allows us to control where we're doing photolithography. And with a DMD device, I can have 22,000 and more, that's the commercial version right now, 22,000 different tips working in parallel, deciding which ones go on and which ones go off at a given time. So now I can begin to independently address and build structures at will over surfaces. That also has become a commercial tool. A company called TerraPrint that we started developed those tools, and those are now used all over the world primarily for research purposes. They're great prototyping tools. And the message for today, though, is really important. If you look at this transition, we're thinking photolithography, fabrication type tools, the way you would as an engineer. But I forgot to leave my chemist hat on, and we should have been thinking earlier, but we are now, that these are the world's most powerful synthesis tools. Each of those tips can be viewed as tiny little fingers, locally controlling reactions underneath. And what that allows you to do is to make materials faster than anybody's ever made on Earth before. And I'll back that up in a second. And build these things you heard about called megalibraries, where we have everything positionally encoded, discrete materials, defined in a library where a mega library on the low end has 1 million different materials. On the high end, the commercial versions now have 56 million. We've made at the university 5 billion. Okay? To put that in perspective, the world, in terms of inorganic materials, has made and characterized less than 1 million new inorganic materials. So in one experiment, you can make orders of magnitude more materials than scientists have cumulatively made to date. And that's, to me, the profound observation in terms of where this is headed and what we can ultimately do with it. And then finally, you can see Toyota comes along, Mirkin comes along, and we recognize, hey, this isn't just brute force synthesis. This also represents an incredible source of big data that can uniquely inform machine learning and AI algorithms. And so now you're kind of off to the races. And the question, of course, is can we gear that towards rapid materials discovery? And so here's the problem. I mean, you guys heard about this already in the sense that, this is a challenge. If you think about the way we discover materials, it's amazing that we're as far as we've gone today. I mean, I'll make 2 arguments today. One is we're pretty good. We use smart people, great synthetic chemists like Tim, use their intuition, come up with something really cool. They make it. If it serves a purpose, we build a plant around it, and we solve a problem and make money from that. When I look at this and think about the small numbers involved, I conclude a couple of things. One is we're going too slow, and 2 is that we have to be working with local maxima as opposed to global maxima. That's something that fits our need at the current point in time, not necessarily the best material for that particular need. And that's critical because then we build as a society an infrastructure around that, and then we're kind of stuck in that. And so the question we've been asking with megalibrary, can we accelerate that? And the answer is yes, as you're going to see. And 2 is then, can we begin to utilize the data from these libraries to begin to train these algorithms so that machines then can begin to objectively tell us where and how to navigate around, Tim's making fun of me, the matterverse. Tim and I were lab mates for a long time, so I can call him out a lot. Or the materials genome, however you want to refer to it. And so at the end of the day, at least what we conclude in this particular space is there are no large scale, high quality data available to train AI for machine learning, or AI and machine learning for accelerating this process. And therefore, it's a relatively slow and expensive process. And we want to figure out if we can change that. Now, that's the good news. The bad news is this is complex. This is even more difficult than the protein folding problem, AlphaFold, right? Why? Because the parameter set is enormous. It depends upon composition, size, shape, phase structure, the structuring within the particles, right? All of that. And you can define even more and more refined parameters that could be important in many different areas. So you have to kind of look at what's really necessary, what's practical versus what's ideal. But if you look at the, and put some constraints on this, our palette is the periodic table. But not everything in the periodic table can be used. Turns out a lot can. I'll show you in a second. It can. Then, if we're talking about nanomaterials and the fact that every material, when miniaturized to the nanoscale, has different properties, we have to look at size and shape, and then compositional changes. And you look at the numbers get very large very fast. I mean, I think it's very easy to look at this 10 to the 14 doesn't look that big. It's a big number. And the actual number is a lot larger than that. So this is a challenge. This is one of the big challenges, I think, in material science today. And so we want to use the mega libraries to dramatically accelerate this process. And so yes, we'll start with intuition. We'll start with smart people like Tim, and we'll go through and make some guesses, make those materials. But then we will begin to train AI and use a combination of smart people and machine learning and algorithms to begin to tell us where to navigate, and then use the tools not as just a data source, but to validate or disprove what we're predicting with those capabilities. That's kind of the theme of today. And the goal is ultimately to build the world's most powerful materials AI. So not a small task. So how do we do it? To me, it's not just about synthesis, right? It's about multiple silos. One is synthesis. So what can we make? I'm going to talk about that, what we can and cannot make with these types of tools. We don't know everything. We know we can make a lot, as it turns out. But making things fast and then slowly sorting through them is not a big step forward. So you also have to, in parallel, develop high-throughput screening capabilities. And that's where this creates a need for some clever ways of thinking about how you get the information out, and then how you collect that data and ultimately inform the algorithms to come up with algorithms that are meaningful and helpful, and validating those, and having kind of a closed-loop system that goes through this process indefinitely is what this is really all about. So I'm going to tell you about each of these silos today. Okay, so how do we think about making materials? How do you do that? Use the tips. There's a cool reaction or set of reactions that we've developed that rely on what I like to refer to as nanoreactors. As chemists, we tend to make things in massively parallel fashion in solution. It's hard to beat the parallel nature of that type of chemistry, but things aren't positionally encoded. And so a lot of people have spent time making colloidal types of particles, and many people in this audience, including also our own group, have spent lots of time coming up with protocols for doing that. Here, what we want to do is control reactions on surfaces, so we have to think about how we can do that. People have thought about how you might do this. Dick Crooks has got some real nice work where he began to use dendrimers, and the idea was that you could put metal ions in those dendrimers, and in solution, not on a surface, locally control the synthesis of a particle with a discrete number of metal atoms and discrete type of metal atoms. The problem with that, of course, is range, both in terms of numbers of atoms and the complexity, the types of atoms that you can include, and also that it's in solution. Other people have come up with interesting ways, Terry Odom at Northwestern, of creating microwells and controlling chemistries within those types of wells, and all of those are really important advances that lay the foundation for some of the things that I'm going to talk about today. We thought about it a different way. We said, how could we use these tips to locally control chemistry? Well, let's create an ink that can be preloaded with metal ions. So polyethylene oxide, poly-2-vinyl pyridine. Block copolymers are great for that. There are people, even here at MIT, that have just made an entire career out of understanding the phase segregation properties of these types of materials and utilizing them to locally control synthesis within a block copolymer type of architecture. We want to use it in a different way. We're simply using it as an ink and a reservoir for metal ions, and the tips then are going to come down and put on a hydrophobic surface, because these are hydrophilic materials, a drop. And that little nano droplet turns out can be attoliters or even yoctoliters. You can look up the prefixes there in terms of volume. These are really, really tiny structures. Become both the solvent and the reactor. Confines where the reaction can take place. And then we go through a protocol of thermal annealing under a reduced environment, blow away the polymer, reduce the metal ions, and if everything works well, all the atoms coalesce to form one tiny particle. And so that's kind of interesting, because it's a reaction where 100% of the reactants go to form one particular product. So keep that in mind. I'll back that up in a second as well. So we go initially with gold, tetrachloroauric acid, for example, as our metal ions. We deposit different sized reactors, and it's really remarkable. You can see on the top line here, 160 nanometer diameter up to about 220 nanometers in diameter. Look at the resulting particle sizes, from about 17 nanometers to about 22 nanometers. So roughly 1/10 the size, or at least the diameter of the reactor, is the diameter of the particle you get. In every single case, a single particle. What that tells you is what you put in the reactor ends up in the particle. I'll prove that, and I think to a greater extent a little bit later on. Those aren't particularly small. Well, how do you go smaller? You reduce the number of metal ions, you reduce the size of the reactor, and you can make smaller particles. So now we're down below 10 nanometers here. Here we actually use polymer pen lithography, made 11 million of these and that gives us incredible statistics. And so you can see that it's 4.8 plus or minus 1/10 of a nanometer. The distribution there is actually tighter than what you would get with some of the best syntheses for gold nanoparticles in solution at this size. And we developed some of those, so it's kind of a comparison of our own protocol. So we're pretty confident about that. And the reason for that is the loading procedure is remarkably reproducible, and the lithography in this case is incredibly reproducible. Each of these reactors are nearly identical in volume. Okay, so the first thing you get out of this is, okay, it works. I can make at least gold particles. The second thing is this is a fantastic surface science tool because now I know where the particles are going to be made. I can set up the reaction the way I want. And in an electron microscope, I can lower the temperature, raise the temperature, and use the beam as my reducing source and follow the process of a particle being born, growing, and evolving to one full entity. So nucleation and growth in this case. And so if you look at this, you can see that these are the little nuclei that form. We've got mini frames becoming a particular movie, and you can see everything within the reactor coalesces to form one particle. Kind of neat. I teach general chemistry and I always felt like a fraud until we took this because I used to talk about the importance of Oswald ripening. I'd never seen Oswald ripening. Well, here you're actually looking at both coalescence and Oswald ripening. They're different. Coalescence, two nuclei coming together and merging to form a bigger particle. Ripening, this guy dissolves, gives up its atoms, so this nuclei, or these set of nuclei can grow. Those are fundamentally different You can actually tease that out of this type of movie and these frames and answer the question, when is coalescence dominating versus ripening? And it turns out it's distance dictated. Greater than 5 nanometers, it's mostly ripening. Less than 5 nanometers in terms of separation of nuclei, it's primarily coalescence. Okay, so the thing you get out of this is not just an interesting movie, but you can actually get incredible fundamental insight in here because you can set the reaction up the way you want and then control the process of going from reactants to product in one experiment. Now I said what you put in the reactor ends up in the particles. How do I know that? Well, here's the first evidence of that. Here we make a 3-component particle. In this case, gold, silver, and nickel. You can see the elemental map here, color-coded. The nickel is green. The gold and silver form an alloy. That's to be expected, right? That's the orangish yellow type of color. And what we've done is we've intentionally kept the ratio 1:1 for gold and silver, but increased the nickel content from 20% to 80% as we go from left to right. And you can clearly see there's a remarkable linear relationship in terms of what we want to do and what we ultimately get. And that's because of what I said. All the reactants go to a product. If that isn't the case, then we're kind of dead in the water. And I'll show you that over and over and over again. This maybe is the most convincing one. So I had a great student, Peng Chen, who then went to Berkeley and is now in China. And I said, look, we really need to prove that we can make things that, Tim couldn't make. It's going to be my theme today. So let's do something really impressive. Let's take 7 elements and make every combination. Single element, 2 element, 3 element, 4 element, 5 element, 6 element, 7 element, and make them and keep them all the same size to show that we have size control as well. And so this is just a subset of that particular library. I'm going to come back to the importance of this in a little bit. The first importance of it, though, is one, it works. All these combinations can be made. 95% of these have never been on the planet before. Okay, so the other thing is you now are making lots of things that we've never made or even considered before. And the structures of these types of materials could not be predicted by the best material scientists in the world. And that's one of the reasons Toyota got involved. I'll come back to that point in a second, because we're going to use this data actually to inform some of the algorithms that I'll be referring to. Okay, what can't we do? Well, I said, look, guys, we should be able to go down to a single atom. Just keep diluting and making smaller and smaller reactors, and pretty soon we should be able to put an atom where we want to put it, and we know where it is because it must be in that reactor. The problem, of course, with that is if you just keep diluting the metal content in the polymer, you have a sampling problem. So when you get to really tiny particles, it's very difficult. You get a much broader range of sizes. So you might get one with one atom, you might get two, you might get three, you might get four, and so on and so forth. So Peng Chen came along and he said, I got a way, I think, to solve this. Let's not use a block copolymer where we have many sites where metal ions can reside. Let's synthesize polymers where we encap them with a single metal containing site, a porphyrin group. And a porphyrin will allow us to put almost any metal that we'd like, at least within the ones that we were looking at the time. And now it's just a matter of controlling the number of polymer chains in a given reactor, the number of ones you mix within a given reactor, to more tightly control both composition and size. And this is kind of neat. So now he can go down to, if you look in the right-hand side here, the reactor roughly called 60 nanometers in diameter. We're using dip pen in this case because we really need to push the resolution down to less than 20 nanometers. That's reactor size. The particle size on the right, you can see they're beautiful. 2 nanometers here. These are gold in this case. 6 nanometers in the upper right, all the way down to less than a single nanometer. Okay, pushing the limits of what we can characterize. The aberration-corrected a microscope cannot tell us the exact number of atoms. In fact, that thing is very dynamic under the beam. So one of the things that's going to really challenge is how you make and study these types of structures and fully get all the information out that you want from them. But the point is we're beginning to come up with clever ways of controlling all the parameters that ultimately matter. Okay, so then you look at this, and we're pretty good with metals, but we'd like to, as I said, use the entire periodic table. And you can look at some of the problems up here above. So the ones in call this salmon color, are easily done by what I've just described, conventional scanning probe block copolymer lithography. The ones in blue have low mobility, more difficult, need different protocols to make them. Some of them have precursors that are hydrolyzable. That's a problem. Incompatibility. Some can't be reduced in hydrogen, and some are just volatile, so they're not amenable to high temperature type syntheses. So if we want to expand the palette, we have to figure out ways to do that. To make a long story short, we now can do that. We've made every single one of these, and I'll talk about a couple of the routes that we use to overcome this problem. You can see all but the radioactive ones, right? We can make those too. We just don't want to go to the expense to do that. There's no inherent reason we couldn't make those. There are a few here. You can see the alkali metals over there, antimony and tellurium. They're not here. Because they're really volatile materials, right? And so they're not amenable to high temperature, but we can mix them with other materials. We've been able to make a binary and ternary type structures with those as well. So we're getting to the point where, for all practical purposes, the bulk of the periodic table can be used in these types of syntheses. And so here you can kind of see the types of structures that are primarily metals or metal oxides that we can routinely work with. These are what I'd call the easiest ones to ultimately work with respect to what I've described to date. Okay, so how do we get information out? How do we actually use these tools to find something of interest? Well, we thought, okay, it would be nice if we could find electrocatalysts. Right? You get nanomaterials. They should be important in catalysis. We can put them on a chip in a positionally encoded way. We can put them on an electrode and drive them all electrochemically. That was one of the reasons we chose electrochemistry as a tool to look at these in mass. And initially, we looked at this not as a way of using megalibraries, but as a way of designing catalysts by taking insight from theory, for example. Chris Wolverton at Northwestern, one of the world's best computational material scientists, was challenged with the idea of looking at all these types of materials we've made, these mini-element systems, which ones would be interesting, for example, for the HER reaction, just as a low-hanging fruit. And he creates, in Computer Row, the volcano plot on the left. And if you're not used to looking at these, this is looking at basically hydrogen affinity to a surface. And no big surprise that platinum is really high. That's the material of choice today. That's what everybody'd like to replace. If you look at the apex here, platinum gold nickel, platinum gold copper had not been considered before. Those are two of the compositions we made. We can make them in mass on a glassy carbon electrode and look at their properties and compare them to the other materials. Well, we made all these. And you can look nickel and copper and gold are all below, as you might expect. You look at the 2 components. Some of the 3 component systems are also down below on the volcano plot as well. When we make these structures, and then we drive them electrochemically, and we just look at overpotential as a quick measure of have we taken a step forward, sideways, or backward. And so we're comparing this now to platinum. So in this bar graph in the upper left, you'd like to be as low as possible. Right at the x-axis is where platinum is. And so I'm looking at this in group meeting, and the guys are all excited about this. They're presenting. It's like, great, you just spent $2 million and you've made a more complicated material that's comparable to platinum. That doesn't seem like a win to me. And they said, no, you don't get it, Chad. They said, we made a material that has 1/7 the platinum. And keeping activity comparable to platinum, but decreasing the reliance on platinum actually is a big deal. In fact, if you could go to getting rid of platinum altogether, it'd be a huge win, even if it's comparable in terms of activity. And I buy that argument. Now, the other thing is I went to Wolverton and I said, well, you're not very good, because you told us that platinum gold nickel is really good and platinum gold copper with your theoretical calculus, which means you can't just totally rely on theory. And so the question is it Wolverton's not good, or our experiment's not very good, or is there the truth somewhere in between? Well, it turns out what's beautiful about this tool is you not only can make catalytically active materials, and they're all positionally encoded, but before, during, and after the reaction, I can go back and look at phase structure. And he looks at it, he said, no, I am pretty good. He said, I modeled these because you told me to model them as alloys. And if you look at these guys, platinum, gold, copper, you can look at that and immediately tell it's an alloy. Everything's mixed. Look at platinum, gold, nickel. It's actually a phase-segregated structure where platinum and nickel are in one domain and gold is in the other domain. So he's actually got a 2-component and a single-component particle, and that on the graph is not a very good set of catalysts. Okay? So what the other thing that I can't emphasize enough is it's not just about finding things, but it's about being able to look at these types of things, understanding their structure, and correlating that ultimately with properties. Okay, what else can you do? Well, we don't know yet what the limitation is. A lot of people, I think even in the audience, are interested in perovskites, halide perovskites. You can't make those under the types of conditions that I talked about, but you can basically make nanoreactors by using low volatility solvents, in this case DMSO and sulfolane mixtures, and putting them on substrates where, again, they bead up, and you can control the volume of the reactor. But if you put the precursors in, you now can affect crystallization at low temperature of these types of materials. And here you can see where we're making 100,000 crystals, all positionally encoded, all single crystals, by the way, in each reactor. And then you can begin to study these types of materials. You can use their optical response as a readout to begin to look at how composition and size correlate, for example, with optical activity. That could be important. Just to give you a feel that this is quite general, whether you're talking about the cation, the halides, or every combination thereof, you can begin to look at these in mass. You can get optical outputs that are really quite nice. Any reasonable region of the spectrum we'd like to access, we can. And then you can begin to ask the question, how do we find something that people really care about? And I'll come to that in a second. But if you're following the point, to this particular point, what we know now is we can make a lot of things. We can make metals, we can make metal oxides, metal sulfides, lots of interesting structures like halide perovskites, quantum dots, upconversion particles. Again, I think as long as you can come up with a combination of solvent/reactor and precursor compatibility, it's fair game in terms of coming up with a synthetic protocol to make these structures in mass. This sets a stage, though, for what I kind of introduced at the beginning of the talk. Can we begin to build massive libraries that allow us to mine the materials genome in a significant way? And you can drive it down different types of screens. The key is, in the early days at least, is you want screens that are really rapid and easy to implement. Primarily optical are the best because you can go in mass and basically just take a photograph using a variety of different types of devices to figure out where the high activity, medium activity, and low activity is. So let's look at that. Take the perovskites. We can generate combinatorial libraries a variety of ways. One is to do gradients. The other is to build a library where we systematically control with one composition particle size, right? Can do that with contact time like I showed you, right? And then we can come in with a laser and within the library, quickly at each site convert into a new composition via ion exchange. In this case, I forget which one this is. Oh, it's bromine loss is initiated by the laser, and we're replacing with chloride. And now we can build both a size and compositional gradient rapidly. And we can begin to look at the optical properties in mass then, and correlate then the optical properties with both composition and size. To make a long story short, you can do this in mass and build these incredible, or just tiny incremental changes in terms of composition, make a huge difference in terms of activity. We discover the highest efficiency blue emitting material using this particular approach. Okay, so you can channel it down particular targets of interest as well. What about the megalibraries? Well, how do you do that? Well, you can build a gradient on the pens. We use spray gradients. Put different types of polymers, for example, with different metal ion contents. And then we can flip that around and now pattern on a substrate of interest. And that creates a gradient of compositions and sizes. We need a way of getting the information out. So the Air Force is looking at this and they say, well, we've got a really slick tool based upon Raman spectroscopy that if you could build a gradient on our posts where they have, it's called an array detector, we can go through quickly and look at each post if there are different compositions and sizes, and begin to scan for catalytic activity. In this case, they're looking for a catalyst for single-walled carbon nanotubes. And they wanted to look at copper and gold, all the different mixtures in terms of sizes and compositional gradients. And the good news about this, you simply look for the signature for the single-walled carbon nanotube and the rate at which it grows to figure out where you have the most active catalysts. And so this is an incredible, way of getting a lot of data quickly. Now, this is really important. You can kind of see here there's a rapid rise to a global maximum here in terms of activity. That turns out to be gold-3 copper. That catalyst was not known before for single-walled carbon nanotubes. That's important point number one. Important point number two is that there are hundreds of catalysts in this library. There's only one global maximum. And it goes back to what I said earlier. I'm convinced as a world we're using what we found that seems to fit the need as opposed to the best material. And ultimately, this is going to allow us, I think, to really go down the path where we find the best materials for a given need. Okay, so now how do you put it all together? That's where Toyota comes in. And so we've got megalibrary synthesis, high throughput screening. And we're not there yet. We're working on all these, and we will be working for the next decade in terms of really creating a massive set of capabilities. But how do you then put this into machine learning and ultimately utilize that to feed the machine, so to speak? So they came to us and they said, let's start with one of the data sets you had. Go back to that 7-element library. You have these incredibly interesting particles. They're unbelievable phase structure. They're all discrete materials. Let's use that structural data, build algorithms that we then can test, and ask, can it predict things first that you've already made? So we take every combination of 4 elements, and it was 100% in terms of predicting it. But you could say that a really good material scientist might be able to do that on their own. What a really good material scientist can't do is take 6 elements and tell you what's going to happen. And in this case, to challenge the algorithm to tell me the combination of 6 elements and the stoichiometries required to make a specific type of particle, a particle that has a single boundary, single phase boundary, so 2 alloyed regions and single phase boundary, and that's the limitation. And that is the most complex single interface nanoparticle ever synthesized. It produced 19 possibilities. We made all of them, and 18 of 19 were correct. And at that point is when I really became a believer in the fact that this type of data is going to be really, really important in terms of informing materials predictions going forward. It's a baby step, but a really important step, because nobody I know on Earth could actually make that type of prediction. And you look at some of these particles, as I said, it becomes a validator. The tools become validators. You can make the particles that the machine predicts at whatever composition you'd like because of all the things that I talked about. And you can ask, what was it correct or not? And these are the types of architectures that were made, the single boundary type systems. Okay, and so where are we headed with this? We clearly are going down a path at the university where we're trying to build these silos, and we built what we call the Center for Nanocombinatorics. But we also started a company called I like to call it MatIQ. They call it Matique. I don't know why. I think MatIQ is a lot better, where matter meets intelligence. Regardless, that's an internal fight we're having. The challenge in terms of turning this into something that can be commercially interesting is, you've got a fire hose of possibilities, picking one common infrastructure. So they've chosen to pick electrocatalysis. So all the libraries can be different, but the driving can be very similar. The data collection can be very similar. And the needs are very large. The world needs better electrocatalysts for making lots of different materials. And in this case, they're driving it heavily down the CO2 to value route. Can I take CO2 as a feedstock and use electrocatalysis to drive it and convert it into things that people need and people ultimately want to sell? And I think it's actually a pretty interesting proposition, and that's an experiment that's going underway. And in 5 years, I'll come back to tell you whether it was really successful or a horrible failure. I want to finish, though, by, first of all, thanking all you guys for showing up. It's a good crowd. But also the people that have done the work. It's my group at Northwestern, and just an incredible team of talented people from all over the world. Anybody wants to do postdocs, write me. If you've got a great skill set that can contribute, we're going to be hiring quite a bit in this area and other areas as well. And then I've mentioned a lot of the key players throughout. Vinayak Dhri, very important on the electron microscopy side of things. The Toyota team's up there as well, and the Air Force team. And then the funding was provided by the groups over there on the left. It's been a really good run. And I said, the Toyota researchers, they found us. We now have the bulk of their budget. They're so excited about this from just an experimental standpoint. It's kid in a candy shop type of thing. I thought, this is going to go nowhere. And these guys went bonkers over this, which was really quite exciting and gratifying that they came independently and found out what we were trying to ultimately accomplish and clearly believe in it. I will stop there and be happy to answer any questions if there are any. Thanks.
Thank you for the wonderful talk. So we have time for a few questions. Let's start here.
Great talk as always, Chad. I have a question about where you're headed with Toyota in terms. Oh, sorry. So I have a question about where you're headed with this collaboration with Toyota in terms of like how you close the loop and then implement these. Is the strategy to identify with this and then figure out in a parallel effort how to make that en masse, in some non-combinatorial way, or is it to continue to print these things? And if so, have you had any successes in that regard yet?
Yeah, it's a great question. So he's hitting on another important point. One thing to discover in a library, another thing to say that, hey, I can scale it up, and what I've discovered is actually meaningful in scaled up form. Really critical part of the whole exercise here. Toyota right now doesn't care about that. Because they're really driven by their AI interest. We do, though, and Matique really does as well. And so, as you guys know, we moved Ted Sargent and Shana Kelly recently to Northwestern. That was by design because Ted is big into that. And so we're working closely with this team. We've actually taken new catalysts for the OER reaction that we've discovered in the megalibraries, where there's a bigger need than even the HER. Where the goal is to come up with a composition that replaces iridium. We've used a 4-element library, and we've found lots of catalysts, like we did before, that actually work, and some that are really, really primo. And we've taken not just the primo ones and scaled them up via synthetic protocols that are related but not identical to this, but some of the intermediate and some of the weaker ones. And then we run them in an electrolyzer, look at their catalytic properties and compare them to what we saw with the library. And there's almost a near linear relationship with a couple of outliers. We don't know why the outliers are there, but it's remarkably consistent, which is the first evidence, significant evidence. We did that with the HER reaction, but an N of 1, where we did 25 different compositions with TED. And I was saying, I think it's really important because it's the first evidence that, hey, what you discover can be scaled up and actually works both qualitatively and quantitatively in similar form. And there'd be all sorts of reasons why that might not be the case, right?
Wonderful. So there are a couple of questions back there, Teddy.
Oh, she's the boss.
Back there.
Have you worked on any applications for solid-state battery at sub-micron or?
No, we haven't. It's a lot of people, I think, want to. I think, look, one of the reasons I'm here is I'm hoping these are tools that lots of people that have different interests that will every one you develop, you have to develop an infrastructure on the screening side. It's not, synthesis, screening, and then if you're going to use AI, the AI side of things. And those have to go in parallel. So it really is just an enormous number of possibilities, which is both an opportunity and a challenge. And so both at the company and the university, we've decided to kind of create common infrastructures. And if you'll notice, the vast majority of our screening protocols are optical, and that's by design. And we're actually taking probes that have been developed in the biological research community that have been designed to look at products of CO2 reduction and that are optical based that can be put on a megalibrary as it's being run electrocatalytically and look at the products that are formed, get activity and selectivity based upon those probes. It doesn't tell you which specific particles, but it tells you where the bulk of the action is. And as you can see with a lot of these, there'll be mini catalysts in that area where there's a bulk of it. But you can take that and then expand it and refine on it and use duplication to converge in on the structures that are the best. But you'd have to do the same on the solid-state battery side of things. And, other people are thinking about looking for new superconductors. You could use a magnetic probe, for example, and use the Meissner effect to scan it as a function of temperature to look at different compositions. Mercuri Condensitatus is very interested in that. I think that's what's so exciting about it. It's such a great challenge from a synthetic standpoint, what's possible, but then how do you actually look at what these things do rapidly is an equally interesting question. It requires a different skill set and a different group of people to do it depending upon what you're searching for.
Wonderful. Yes.
Thank you. It's very interesting. I'm also particularly interested in terms of nanoparticles using multiple elements. So but it seems like those nanoparticles are just like phase separated, not single phase. Is there any interest exploring whether you can make a single phase or high entropy alloy based on your method developed?
Well, you can, and these are thermodynamic, so we drive them to the endpoint, go to high temperature. But you can look at them, we have looked at them every step of the way. You kinetically trap them. Whether you have a single phase or a complex heterostructure like we have, a lot of it depends upon the choice of elements, the number of elements, and then the conditions you use to drive it from precursor to product.
Thank you.
So how do you choose to which area of or which chemical space would you want to look at for a particular application?
Well, again, so he said, how do you choose, which phase space or chemical composition space we look at for a particular application? You go into, take the OER reaction. We know iridium's king. We know that the world would love to get rid of it or replace iridium. There's not enough around it to meet the projected needs. So the price of iridium is going through the roof. So you ask, okay, what things could we use that might potentially replace? There's some insight from people going serially looking, and you say, okay, let's incorporate those. But we don't want to ignore things that they haven't looked at. So we make, there's a big, the commercial libraries now have 56 million particles, right? So there's a tremendous amount of landscape you can look at in a mega library. And so it's a combination of what we get from intuition and what the world knows, but also supplementing with a lot of things that might take us down a path that the world hasn't explored. And so that's just trial and error. And then once you get going with that, the idea, at least conceptually, is that the machine, the trained machine, which gets smarter and smarter with the more data that you add, will be your objective decider. I mean, one of the problems with using smart people like Tim to do this is that they have biases, right? Doesn't think that way, but they have biases. They think they've got a bead on it, and that's, you know, a lot of smart people are really right. I mean, it's a good thing. But the machine learning, if it's educated enough, it just doesn't care what the outcome is. It's going to use what it has to tell you what its best guess is.
Okay, thank you.
Let's take one more question.
Thank you for sharing your work. Beautiful. I had a quick question on the rate of, say, printing and then optical characterization and then going back in the loop. You've mentioned using confocal systems, and some of the scale bars are large millimeter, you know, printouts. So is it happening at like a raster scanning format, or is there a capability to do one?
It's right now. Those are raster scanning. So if we look at, for example, with the probes, then we can take an entire image of the chip and just look at color gradients to know where to look and refine. But with the perovskites, that's raster scanning.
I see. So the rate is kind of
to make the particles. To make the particles. To screen them, you can look at them in mass optically. You just look at different colors, right?
Yeah. Okay.
And intensity.
Yeah. Thank you.
Great. So it's past 4, so let's thank Chad for the wonderful talk. So there is going to be a reception in the same room. So Chad will be around for a little while. So if you have any questions that you didn't get to ask, he'll be here to answer your questions.